Well, everyone, welcome back to Math 221. Um, we're just at the beginning of week 9 right now, so we've got 2 weeks of content left before the final. Um, Later this week, I should be sending out a survey to the class to sort of ask about final scheduling, because I know some of you have emailed me about this, but for those who haven't, since we're an asynchronous course, Cal Poly doesn't actually provide us a final time slot, and it's sort of open to us to schedule. Um, my thoughts right now is it will be structured similarly to the exam you took last week. Um, I'll upload it, say, Monday, and it will be due Wednesday. Or maybe I'll upload it Wednesday, it'll be due Friday. I'll send out an email um, to you guys sort of asking about what sort of 3 day block would work best for everyone. And then, I'll sort of aggregate that data together um, and get an answer to you guys. With that sort of bookkeeping out of the way, we can sort of start to look at what we're going to be talking about. We spent the last 8 weeks sort of developing this idea of the limit, and then we used the limit to give us derivatives, um, and sort of developed differential calculus. If you remember, we talked about sort of this wider picture a while ago. Um, and with these last 2 weeks, we're going to turn our attention to the sort of other side of calculus called integral calculus. And in order to do that, we're going to start actually by looking again at derivatives, weirdly enough. Um, and and rather than sort of taking a look at more tools to take derivatives, we've actually kind of looked at almost all the tools you need to take the derivative of any function. Um, we're going to look at going the other way, right? We sort of motivated our original discussion of derivatives, asking, if we know the position of this train, right? We sort of talked about this very quickly moving train. If we know its position at any time, can we find its velocity? And now we actually want to ask the reverse question. If we know the velocity at any time t, do we know its position? Given a derivative, can we find its sort of opposite derivative, its antiderivative? And just to formalize that in a definition, it's exactly what you would think it is, right? A function f is an antiderivative um, of some function little f, right? On an interval capital I, um, if the derivative of capital F equals little f for all little x in my interval I. And we'll get into actual ways to compute these in a second. But I want to just sort of start out thinking about the properties of the derivative and what necessarily must be true about antiderivatives, right? The first thing, right? We can say in some examples, we can say x squared is an antiderivative of 2x. Why? Well, d dx of x squared is 2x, right? But here's what I sort of want you to notice of this, right? Clearly, if I give you a function, you can take its derivative and be like, hey, well, since the derivative of x squared is 2x, x squared is the antiderivative of 2x. But a thing to notice here, right, is, well, I guess I'll put this in green, x squared plus 1 is also an antiderivative of 2x. Why? Well, simple. If I take its derivative, that 1 is going to go away, so I'm still going to get 2x. And, this is where things start to get a little bit more complicated than they were when we were taking straight derivatives, because now 2x has more than one antiderivative. You know what? Let's look at a function that is a little bit simpler, right? And we can ask, what are the antiderivatives of IVES derivatives? Let's just say f of x equals 1, right? What functions can we take the derivative of and get 1? Well, let's think about this, right? If we take d dx of x, well, that's going to be 1. As we saw in the last one, if we were to say take the derivative of x plus 1, well, that's also going to give us 1. We could do x plus 2. In fact, we can take the derivative of anything that looks like x plus c equals 1 for any real number c. Right? C is any real number. If I add it to the end of this function, we're going to get 1. And this actually leads us directly into a theorem, which we're going to, as usual, state without proof, but this is the basic idea behind it that we've just talked about. Okay, and so we can say let G be an antiderivative of f on an interval I, then every antiderivative f, capital F of little f, on my interval must be of the form capital F of x equals capital G of x plus c, right? Where again c is our constant. And so what this is saying is, once we know one antiderivative, right, we can form the whole family of them by taking that original antiderivative and then adding some constant. Maybe that constant is 1, 2, pi, e squared. It can be anything, right? Which means there are an infinite number of antiderivatives. Of our function f of x equals 1, there's an infinite number of antiderivatives. We can add any real number to our antiderivative x. For our function 2x, well, we know x squared is an antiderivative, right? Just realized that is an anti. I sort of double used the word and there. But since x squared is an antiderivative, all of the antiderivatives of 2x look like x squared plus c. Okay. And with this theorem, right, we can actually start to work towards developing this idea of taking antiderivatives. Okay. this process, right, of taking antiderivatives or finding all antiderivatives of a function. It's called antidifferentiation, um, or it's called integration, right? This is where the phrase integral calculus comes from, right? And we use this very famous sign, antidifferentiation. And then, we use this very famous sign, this integral sign here. Looks sort of like a big, sort of very thin and then stretched out S in a way. And we write it like this, right? If we're taking the integral, right, of f of x, right, we're looking for the antiderivative. We put this guy before it to sort of say, hey, we're taking the antiderivative, and then the dx tells us with respect to what, right? If you're sort of thinking about in terms of the like derivative language, right? This integral sign here corresponds to my d, sort of, and this dx and this dx, go together, right? So you would read this, right? The indefinite integral of f of x with respect to x, equals f of x plus c. Okay. And what this is telling us is that our indefinite integral, or our antiderivative of f of x, right? This guy f of x, this is called our integrand, right? And then c is our constant of integration. And so this is language that we will get used to over the next 2 weeks, and sort of use throughout homework and then on the final, of course, as well. One note: I know on some of the homeworks and the quizzes, you guys will drop the sort of limit expression before things. I've been fairly lenient with that. You definitely can't drop this integral sign. It would be sort of like not adding the plus sign when you're adding two numbers. Like, this is telling us what exactly we're doing, right? And we've already found two antiderivatives, and so we know, based on the work that we've already done, that the antiderivative of 1 with respect to x, right? We know that's x plus c, right? We know that the antiderivative of 2x, we found that's x squared plus c. And so now our question is, what else can we know, right? What are the sort of rules of taking these antiderivatives? And we'll start with rule 1, which is for constants. And for the majority of these rules, since derivatives and integrals are reverse operations, right, much like addition and subtraction or what have you, the best way to find these rules is to make an educated guess and then confirm by taking derivatives, right? So for constants, right, the integral of some constant k with respect to x, well, what should we expect it to be? What about something like kx plus c, right, where again k is our constant? And we can sort of check this right, by taking my derivative of kx plus c, and, well, my c is going to drop away, my x is going to drop, and we're just left with k, which is exactly what we wanted. So our guess was good. And, we can do two quick examples of this. This is one of the, ones that's a little bit easier to wrap our heads around, right? The integral of 2x dx, or sorry, the integral of 2 dx is 2x plus c, right? Just following this rule. And maybe the integral of pi squared dx, well, it's pi squared x plus c. You'll notice sometimes, textbook authors or lecturers or exam writers will use really weird constants, pi squared, pi times e, pi to the e, whatever, as a sort of hint of, hey, this constant is very strange, but it's not actually going to matter to the problem, and I'm showing you that by using such a weird constant, right? On the last exam, there was a pi squared, I think on the first question, but it didn't affect anything because it just dropped away once you took a derivative. The next thing to look at is rule 2, the power rule, right? We know that my derivative of x to the n, right, is nx to the n minus 1. So what should we guess is the integral of x to the n dx? Well, it's going to come out to 1 over n plus 1, x to the n plus 1, plus c. And there's two sort of important notes here. One, n can't equal negative 1. We'll talk about what happens when n equals negative 1 here in a bit. But the other is that this guy seems a little bit strange, right? But use this rule right here. Our n minus 1 drops down. We get n minus 1 over n minus 1 for 1. Then we subtract 1 from my exponent when we're taking the derivative, and we're left with x to the n, right? So this does hold, right? We also need our constant of integration there, our plus c, right? And I am aware that this one is a little bit less intuitive than the other one. It takes a little bit of getting used to. But let's practice with something like the antiderivative of x cubed, right? The antiderivative of x cubed, well, we need to 1 over n plus 1, so 1 over 4, x to the 4th. And again, we can't forget this plus c. Super easy to forget our plus c. But if I were to take the derivative of this, 4 drops down and we get x cubed. We can also look at something like, the antiderivative of x to the 3 halves. Well, once again, sort of just, following with our steps, we're going to get 1 over 3 halves plus 1. So 1 over 5 halves, x to the 5 halves, plus c. Or we can simplify that one step, 2/5 x to the 5 halves, plus c, right? And then I'll let you pause and work through this guy, the antiderivative of 1 over x to the 3 halves. Work that guy through, and don't forget your plus c, okay? The next rule, the technical name for this rule, according to your book, is the indefinite integral of a constant multiple of a function. That's kind of a mouthful. So we're just going to call it the constant multiple rule, right? This has to do with the fact that if we're taking the derivative of c times f of x, well, that is c times the derivative, right? And it works through the way you would think, right? Since these are opposite operations, right? They undo each other. Working with these educated guesses is, often the way to go. And the antiderivative of c times f of x dx, well, I can pull this constant out, right? Now it's very important, right? This is not how it works, right? Say if we're doing something like this is not true, moving this x squared out. Why? Well, x squared and dx sort of have to do with each other, right? X squared isn't a constant, right? And so you can't pull it out, right? So that's not true, but something like 3x squared dx, right? That is equal to 3 times the integral of x squared dx, right? It's very important not to make this mistake, and it's super easy to, right? Because you're like, oh, well, if I can just pluck things out front, why don't I do this? And then the antiderivative of 1 is just x plus c. But again, that's not the case, and it's a super easy mistake to make. And we can work this guy through, right? 3. Well, what's the antiderivative of x squared? It's going to be 1 over 2 plus 1 for 3, x cubed plus c. And then when we distribute in this 3, we're going to get x cubed plus 3c, right? But c is just some arbitrary constant, right? And so, this c you can sort of think of as absorbing that 3, and well, we can just get rid of it, right? Because 3 times an arbitrary constant is, well, it's still an arbitrary constant, right? One more of these. Maybe we'll look at, now we'll go minus 3, x to the minus 2, right? See what happens if we throw in some negatives. Well, that negative 3 is going to just sort of drop through. We get negative 3 times the antiderivative of x to the minus 2 dx. So we have negative 3 times, well, we're going to have 1 over minus 2 plus 1, so minus 1, x to the minus 2 plus 1, so minus 1, plus c, right? When we multiply this guy in, we're going to get 3 over x, and then once again 3 times c is just c, right? And all of these can, of course, be checked via taking a derivative and confirming that we are indeed working with these being antiderivatives. Up next, we'll call this rule 4, the sum and difference rule. Right. And that says that the antiderivative of f of x plus or minus g of x with respect to x Well, that's the antiderivative of f of x dx, and then, the related plus or minus the antiderivative of g of x dx, right? If it's plus here, then it's plus here. If it's minus in the first one, it's minus in the second one. And, this sort of extension over pluses and minuses, well, that's what allows us to say take the antiderivative of something that's a little bit more complex, right? Maybe 3x to the fifth plus 4x to the 3 halves minus 2x to the minus 1 half, all with respect to x, right? And by extending with this exact idea, I can break this up, right? The integral of 3x to the fifth dx plus 4x to the 3 halves minus the antiderivative of 2x to the minus 1 half dx. And then we can apply actually the previous rule, 3 times the antiderivative of x to the fifth dx plus 4 times the antiderivative of x to the 3 halves dx minus 2 times the antiderivative of minus 1 half dx, right? And then each of these I can sort of evaluate on their own, right? 3 times, looks like it's going to be 1 over 6 x to the sixth plus 4 times, we saw this one already, 2 over 5 x to the 5 halves minus 2 times what? Well, we're going to have 1 over minus 1 half plus 1, so 1 over 1 half x to the 1 half, and then a single plus c. Very similarly to what was happening before, right? This is going to give us a plus c, this one's going to give us a plus c, this one's going to give us a plus c, but we can lump all of those together in one constant, right? And as we simplify this, right, 3 times 1/6 is 1 half, x to the sixth. 4 times 2/5 is 8/5, x to the 5 halves. 1 over 1 half is 2, so we're minus 4 x to the 1 half plus c, right? And again, if you go through and take a derivative of this guy, you'll indeed get the polynomial that we started with. Or rather, this is not quite a polynomial because polynomials need integer powers. Building off of what we did over the last 2 weeks, actually, is rule 5. We'll just call it the exponential. And it states that the antiderivative of e to the x dx, well, it's e to the x plus c, right? If the derivative of e to the x is e to the x, well, then the antiderivative would be e to the x, again, plus our constant of integration, right? And we can sort of combine this with what we've been doing before. Say, take a look at the antiderivative of 2 e to the x minus x cubed dx. We can, split this linearly across to get the integral of 2e to the x dx minus x cubed dx, which is 2 times the antiderivative of e to the x minus the antiderivative of x cubed, and then from here 2e to the x minus 1/4 x to the fourth plus our constant c. Our last rule is actually a very special case, and it's what happens when x equals -1, right? We said for the power rule, x can't be -1. Well, this is what happens when x is -1, right? If we're taking the integral of x to the -1 dx, here's my question. What should this be, right? What function, when you take the derivative, gives you 1 over x? Well, it's the natural log of the absolute value of x plus c, right? And of course we know x can't equal 0, right? Because the natural log of 0 is undefined and 1 over 0 is also undefined. And it's very important not to forget these absolute value bars, because it's very easy to write these as parentheses, but according to our rule, it is actually absolute value, right? And part of that is that, well, the domain of 1 over x includes negative numbers, and the domain of just the log of x does not. But once you take the absolute value, everything is positive, and we're good, right? And this allows us to look at the antiderivative of something like 2x plus 3 over x plus 4 over x squared dx. And as before, we can sort of split this across the terms, right? I'm going to split across addition and constants at the same time, just to save us a little bit of room, right? So it's going to be 2 times the integral of x dx plus 3 times the antiderivative of 1 over x dx plus 4 times the antiderivative of 1 over x squared. Or rather, I'll write this as x to the -2 dx. And we can work through these a step at a time. We're going to get 2 times 1 over 2x squared plus 3 times the natural log of the absolute value of x plus, and this is where we actually have to be a little bit careful. It's very, very tempting to try and fit this guy into the framework of that one, right? But it's important, right? This is a power rule because we have a power that's not -1, right? And so we need to use the power rule. It's going to be 4 times -2 plus 1 is -1, and then -2 plus 1 is -1. And then we need our plus c there at the end. And as we give this one final step of simplification, we're going to get x squared plus 3 times the natural log of the absolute value of x. My absolute value bars were a little round there. Minus 4 over x plus c. Now that we have the tools of antiderivatives, we can actually turn our attention to that question that we asked right at the beginning, right? Given the derivative of a function, can we find the function itself, right? And this is the most elementary form of what's called a differential equation, right? And the differential equation asks, well, if f prime of x is 2x minus 1, what is f of x, right? F of x is then the antiderivative of the derivative of f of x dx, right? Because our antiderivative and our derivative naturally undo each other, right? So, that's going to be the antiderivative of plugging in f prime of x, 2x plus 1 dx. And then from here, we can split this up. The antiderivative of 2x is x squared. The antiderivative of -1 is -x. And then we need to add c, right? And, thus there's an infinite number of solutions, okay? And so essentially what this is saying, right, is if our slope is given by this, right, the set of all solutions looks like this, right? A solution to a differential equation, such as this one, right, uh, is any function that solves it. This is a family of solutions, right? Because we have this plus c. That differs from something like a particular solution, right? A particular solution uh, doesn't have a c at the end. It has, some number, right? Think about it this way, right? All functions like this have 2x minus 1 as their slope, right? But say we want, rather than all of them, say we want a particular solution, right? Say we know some point that this graph has to pass through, right? Thinking about this in terms of pictures, right? We know it's going to look at something like x squared minus x plus c. But say we know, right, that f of 1 has to equal 3, right? We know 1, 3 is on our function f for whatever reason, right? We'll do an example here in a second of one particular one. But since we know that, we can actually solve for our particular solution that corresponds to this point, right? Since we know f of 1 is 1 squared minus 1 plus c, which is equal to c. But since we know f of 1 equals 3, that implies that c equals 3. So our particular solution in this case is going to be f of x is x squared minus x plus 3, right? And this parabola would look something like this, okay? And at this point, right, it has that slope. But notice, right, since this plus c is going to shift this parabola vertically, any like vertical shift of this parabola is going to have the necessary slope. But only one of them, our particular solution, satisfies or passes through this point, right? And again, I know that's a little bit not what we're used to, right? It's an example of something called an initial value problem, right? So say we know the following, right? F prime of x is 3x squared minus 4x plus 8, and f of x, or sorry, f of 1 is 9, right? We know these two pieces of information, and we can actually ask, what is f of x? Well, just as before, we know that f of x is the antiderivative of its own derivative, right, because they undo each other. So it's the antiderivative of 3x squared minus 4x plus 8. Well, the antiderivative of 3x squared is going to be x cubed. The antiderivative of minus 4x, right? The antiderivative of x is 1/2 x squared. And so that 4 is going to get divided by 2. We have 2x squared. We have 8x. And then we need to add c. But we know f of 1 equals 9. So What's f of 1? Well, we have 1 cubed minus 2 times 1 plus 8 plus c equals 9. But this means that c plus 7 equals 9, or c equals 2, right? Thus, we can say f of x is x cubed minus 2x squared plus 8x plus 2, because we found a value of c. Right? This idea of differential equations and these initial value problems, there's whole courses about evaluating different types of problems like this. They're all over sciences. There's a ton of them in physics and engineering, especially. Maybe we're looking at something like back to that maglev problem, right? Say we know that the velocity of the train, right, is given by v of t is 8t, right, in our domain between 0 and 30 seconds. And then say that we know that it started at wherever our origin is, right? It started at place 0. So can we figure out how far it's moved? Well, this is actually an initial value problem as well, right? And this is because of two things. One, if s is our position function, right, the derivative of the position is the velocity, which is 8t, and since it started at position 0, it's 0. And this is now an initial value problem, right? And so we can set it up and solve it just like we did before. S of t, we want to find the antiderivative of our velocity function, right? To find the antiderivative of t, right, we're going to divide 8 by 2 and then square it. So we should be getting 4t squared plus some constant c. But we know one more piece of information, right? We need to find the value of this arbitrary constant c, and we can do that with this, right? We know s of 0 is 4 times 0 squared plus c, which is just equal to c. But s of 0 is equal to 0, so c equals 0, right? Thus, my position function must be 4t squared.